lesson's about radioactive decay. Here are your objectives. Radioactive decay, or radioactivity, refers to the radiation of particles and energy from the nucleus, and it was first discovered in the late 1800s when uranium salts were found to fog photographic paper in the same way that light does, and it was subsequently categorized in a number of different ways and grouped into three classes: alpha, which gets this Greek symbol, beta, and gamma. Alpha radiation is stopped by paper, and it turns out that alpha radiation consists of helium nuclei, fast-moving helium nuclei. Beta radiation will pass through paper but is stopped by a thin sheet of aluminum, and it turns out to be fast-moving electrons. Now, these are not electrons from orbiting around the nucleus, they're actually electrons that are emitted from the nucleus itself. So beta particles are fast-moving electrons from the nucleus. And gamma radiation is only stopped by several centimeters of lead. And gamma radiation consists of photons. In other words, it's high-energy light. You can also take a radioactive source, let's say something that is decaying, into alpha, beta, and gamma radiation, and put it in an external magnetic field, and you'll see that the three do three different things. Gamma radiation made of photons passes straight through. It is undeflected by an external magnetic field. Here we see an external magnetic field that is pointed into the page. In contrast, alpha particles, being positive, will, if you use the right-hand rule, be deflected towards the top of the page here. And beta particles, being negative, will be deflected towards the bottom, and because electrons are much less massive than helium nuclei, they will turn more sharply like this. So you can categorize them by what they're stopped by. These are the different particles in each of the kinds of radiation, and you can also see that those particles are deflected differently or not deflected at all by an external magnetic field. Now let's take a look at each in turn in more detail. First, we'll look at alpha decay. So here we have radon, which is a gas that's often found in basements, and it's going to decay into polonium. Polonium has 84 protons and a total of 218 nucleons, as well as an alpha particle, which is a helium nucleus. So this here is an alpha particle, and therefore it's sometimes also written like this. So radon here is decaying here into polonium and an alpha particle, and this can actually be a significant source of radiation in many households. Something to notice, that the number of nucleons on both sides of the equation is equal. So 218 plus 4 is equal to 222. And also the charge on each side is the same. Here we have 84 positive charges and 2 positive charges, and on the other side we have 84 plus 2 is 86 positive charges. So we have conservation of nucleon number. That's what we see in those top numbers, that the number of nucleons on the left and the right are the same. And we also have conservation of charge, where we have 86 positive charges on both sides. So this is a nuclear reaction here for the alpha decay of radon, and just like we will see with all nuclear reactions, we have to observe conservation of nucleon number and charge. By the way, the radon here would be called the parent nucleus, and the polonium would be the daughter nucleus. Also interesting to note that the mass of the stuff on the right side here is actually less than the mass on the left side of this equation. So we've lost mass as we go through this reaction. Here we've got more mass, and on the right-hand side we've got less. So how can that happen? How can we lose mass? Well, the mass hasn't disappeared. It's showing up as energy here on the right side, specifically as the kinetic energy of the products. And how is that possible? Well, Einstein's famous relation E is equal to mc squared tells us that energy and mass are two sides of the same coin. Mass is actually a reflection of how much energy something has. It's sometimes described as mass being a form of frozen or congealed energy. And if you therefore lose a little bit of mass, as is happening here and going from the left to the right, you can get out a lot of energy because of this enormous conversion factor, c squared, or the speed of light squared. We'll explore this more in the next lesson, but just to understand for now that in each of these cases of spontaneous radioactive decay, we're going from more mass to less mass, and that results in the release of energy because of this relationship. More to come in the next lesson. Now let's look at beta decay. Here we have a carbon-14 nucleus, and this is an example of having too many neutrons. If we were thinking about the chart of the nuclides from the previous lesson, where we had the number of protons on the x-axis and the number of neutrons on the y-axis, and this was the line where protons and neutrons were equal, we saw that the line of stable nuclei curves upwards, so that as we get to larger numbers of protons, we have to have more neutrons to hold the whole thing together by the strong nuclear force. We also said that up here, we've got too many neutrons for the number of protons, and so that's the example that we're looking at here. So here, carbon-14 can decay into nitrogen, which has 7 protons and 7 neutrons, giving it a nucleon number of 14, by giving off an electron. Now, the electron has virtually no mass compared to a nucleon. An electron has a mass of about 1/2000th of a neutron or a proton, so we can write that as 0, but it does have a charge of -1, so we write that here. Notice again that we have conservation of charge. 7 plus -1 is equal to 6, and we also have conservation of nucleon number. 14 plus 0 is equal to 14. Now this electron, it's important to note, is from the nucleus. This is not a regular orbiting electron. And to distinguish it from one from the nucleus, we sometimes call it a beta minus particle, so you'll see it written like this sometimes as well. Now there's one more part to this equation for beta decay, but to understand it, let's back up to alpha decay. Remember that we said that we have a decrease in mass moving from the left to the right, and then that mass is shown as energy on the right-hand side here because of this relationship between mass and energy. Specifically, it shows up as the kinetic energy of the products, and because the alpha particle is so much smaller, really we see it as the kinetic energy of the alpha particle. Now the change in mass is the same every time. It's discrete, and that means that the change in energy is the same every time as well. So we only measure discrete kinetic energies for this alpha particle. We'll see the same kinetic energy every time because there's the same change in mass. Now there's the same change in mass down here in the beta decay as well, going from the left to the right-hand side. So we might expect that we would see the same change in energy, the same kinetic energy for the beta particle every time as well. But it turns out that we don't. If you measure the kinetic energy of the beta particle, you see a continuous range of kinetic energies. So what's going on there? Well, in order to make sense of that, scientists had to postulate the existence of another initially undetected particle. And in this case, it's called an electron antineutrino. So this electron antineutrino is sharing the kinetic energy that is resulting from the decrease in mass as we go from the left to the right-hand side. And because the kinetic energy is being shared between these two particles, if you only measure the kinetic energy of the beta particle, the electron, it's going to look like it varies continuously. But if you were able to measure the kinetic energy of the two of them together, you'd see that it's always the same. However, you can't measure this one because you don't detect it. So that's how we know that there's this other particle here. Now exactly why it's an electron antineutrino is going to have to wait for another lesson when we talk about more conservation laws. And just a note about the symbols here, this is not a V, it's a Greek symbol nu, but it looks like a V, and the little bar on the top means that it's an antineutrino, and the little e means it's an electron antineutrino. Again, exactly why it's that, we'll have to wait for another lesson. Now, if we were able to peer inside the nucleus, what we'd see is that we have a neutron that is changing into a proton with the emission of this beta particle and the electron antineutrino. And if we were to put the numbers here, the electron antineutrino has no charge and no mass. So this is what's going on in this reaction, and we call this beta minus decay, where here we see that we have the changing of a neutron into a proton with the emission of a beta particle. Now there's also beta plus decay, and let's illustrate that now. In beta plus decay, instead of having too many neutrons like up here, you have too many protons like you're down here. So here's an example. We have carbon 11, and it can decay into boron like this with the emission of a positron. Now a positron has a charge of +1. It's the antiparticle of an electron, so it has the same mass but opposite charge to an electron. And it can be written as a beta plus particle. Again, same mass but opposite charge to an electron, and we call this a positron. And in this case, we have again the emission of something like this. However, in this case, it's an electron neutrino, not an antineutrino. And again, why that's the case is going to have to wait for another lesson. Peering inside the nucleus, what we see is that we've got a proton that is decaying into a neutron, which has a nucleon number of 1, no charge, with the emission of a positron, I'm going to write that like this, and an electron neutrino. Again, this is beta plus decay. There's another nuclear reaction that can happen when a nuclide has too many protons, and that's called electron capture, and that's shown here. So what happens in electron capture is that the nuclide captures one of the electrons that's orbiting it, and using that changes a proton and that electron into a neutron. Let's take a look. We've got nickel here and an electron. Usually this is an electron that is one of the innermost electrons orbiting the nucleus. And in this reaction, we're going to get cobalt, which has 27 protons and a total of 59 nucleons, and using conservation of charge, we see that we've actually already balanced. 28 minus 1 is equal to 27, and conservation of nucleon number were balanced as well. Now, it turns out that here, as above, we get an electron neutrino. Again, we'll have to talk about conservation of lepton number in a future lesson to understand why that's the case. But peering inside the nucleus, what we have is a proton and an electron reacting. Here we get a neutron and this electron neutrino. Again, 1 plus 0 gives you 1, and 1 minus 1 gives you 0. So we've got conservation of nucleon number and conservation of charge. That's electron capture, another way of dealing with too many protons. Finally, there's also gamma decay. In gamma decay, we don't have a change in the number of protons or neutrons like we've seen above, and we don't have release of an alpha particle. What we have is just release of energy in the form of a photon. So this little asterisk here means that the nucleus is in an excited state. And often that's as a result of previous decays that have gotten us here. So the nucleus itself has energy levels, and it can decay from this excited state to just a stable non-excited state, and therefore we don't have the asterisk here anymore. But to do that, it has to give off energy, and that energy is given off as a gamma ray. Again, gamma rays consist of photons. Now here we have a discrete change in energy, and so we're going to have a discrete energy seen in the gamma ray, just like we saw with alpha decay, in contrast to the continuous range of energies we saw with beta decay. So that's an introduction to the different forms of radioactive decay.